Okay, hello. All right, let's begin. Check if this is visible. Seems to be working. Okay, so here's the lesson for today. We'll just go through some of the theorems and proofs from section 3.3. I know we've done this before, but a student requested that we go through them, so I'm just going through them. Okay, so here's the idea. Before we start, I should actually just recap a little bit about the linear independence. And the idea was that if you have a vector space and if you've made a subspace by making linear combinations of, let's say, two vectors, and if you've already made a subspace and if you want to add another vector to it, right? So let's suppose if you want to expand it and if you have another x3. Now if x3 can be written as a linear combination of x1 and x2, then x3 will already be part of the space and the space won't get expanded. But if x3 can't be written as a linear combination of x1 and x2, then your space will get expanded and all the linear combinations with x3 as well will get added to your subspace. And the idea was that we say, and to define it, to define linear independence, we say that a set of vectors v1 to vn are linearly independent if and only if we have the following. So linearly independent if such that c1 v1 plus c2 v2 plus dot 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 up until cn vn, that is, we take some linear combination of these vi's, all of these from v1 to vn, and if the result is 0, this result can only be 0 if and only if. So if this is 0 and if the set of vectors are linearly independent, this is only possible if c1, c2, c3 up until cn, all of these coefficients are 0. So if even one of these coefficients is non-zero and the result is 0, then you don't have linear independence, right? Okay. So let's talk about a theorem. So the first theorem is that if v1 to vn span a vector space V, so span means you take linear combinations of all of these and they span this vector space V, and one of these vectors can be written as a linear combination of the other n minus 1 vectors, then those n minus 1 vectors also span V. And so here's the idea. The idea is that if you can write one of these vectors, so let's suppose the first thing that we have, let's prove 1, so this is the proof of 1, and the idea is that V, any vector in this vector space V, can be written as a linear combination of alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn, right? And so the statement is saying, the statement of the theorem is saying that if one of these can be written as a linear combination of the other n minus 1. So let's suppose we take a vi from these. So for some i, vi can be written as c1 v1 plus c2 v2, and we exclude vi but up until, so these are just n minus 1 vectors, by the way. They are not n vectors anymore, these are n minus 1. And so cn minus 1 vn, there is one coefficient and one vector missing here, right? So that's ci. So we don't have ci and vi. And so these are n minus 1 coefficients. And what we are saying is that vi can be written as a linear combination of these ones. And so the idea is that now if you look at this v, if I take this vector v and I write it as alpha 1 v1 plus alpha 2 v2 plus some, at some point we have here alpha I vi in this equation, right? Plus dot 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 alpha n vn. So the idea is this alpha I vi, since vi can be written in terms of v1, v2 up until vn, we can remove this vi and instead write alpha 1 v1 plus alpha 2 v2 plus, instead of this vi I can just write c1 v1 plus c2 v2 up until cn minus 1 vn plus dot 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 alpha n vn. And what you have is, now I can take the coefficients common, so v1 I can take common from this one, so I have alpha 1 plus the coefficient, this would be alpha I c1 v1, so I've taken this c1 and this c1 common, and then alpha 2 plus alpha I c2 v2, so on, and you will get rid of this term because all of these coefficients will be gathered in the corresponding v1, v2 up until vn. So at the end you have alpha n plus cn minus 1 plus cn minus 1 times alpha I vn. So what you've essentially done is you've taken any vector in the vector space V and you've written it in terms of v1 to vn, except notice that there is no vi here. And so what you've done is you've shown that this v can be expressed as a linear combination of n minus 1 vectors. And so the idea is that the n minus 1 vectors from v1 to vn excluding vi also span v, because any vector in V can be written as a linear combination of these vectors. Okay, so that's the proof of 1. Proof of 2. So for 2, the statement says something that given n vectors v1 to vn, it is possible to write one of the vectors as a linear combination of the other n minus 1 vectors if and only if there exist scalars c1 to cn not all 0 such that this conditions hold. So what is it saying? It's saying for some one of the vectors can be written as a linear combination, or rather as a unique, to write one of the vectors as a unique linear combination, as a linear combination of the other. And let me just write this as a unique linear combination of the other n minus 1 vectors. You can do this if and only if you have this condition to be true, that there exists C1 up until Cn not all 0 such that C1 v1 plus C2 v2 plus dot 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 Cn vn is equals to 0. So these are not all 0 and yet their linear combination is also 0. And so let's try to prove this now. So one way, so we can go this way, that we consider that you can write it as 0, you can write this condition holds such that these are not 0, and to show that you can write one of the vectors as a linear combination of the n minus 1 other vectors. Or we can go in this direction and say that you can write it as a unique linear combination of the other n minus 1 vectors, and then show that this condition holds, right? And so first let's start from this to this, right? So let's go in this direction and show that if this condition holds, that I can write them as a unique linear combination of the other. So let's suppose these are not 0, then this is fairly simple. I'm assuming that this is true, so there exists C1 up until Cn not all 0, such that C1 V1 plus dot 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 Cn Vn is equals to 0. Now it's very easy to see that I can just pick any one of them and write it as a linear combination of the others by moving it to the other side. So let's say I pick Ci Vi and I move the rest of them to the other side. So minus C1 V1 minus C2 V2 dot 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 minus Cn Vn. And so notice that Vi can be written as minus C1 over Ci V1 minus C2 over Ci V2 dot 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 minus Cn Vn over Ci. And so since this exists, we've seen that we can write it as a linear combination. We can write Vi as a linear combination of these other vectors. Okay? And so that's the proof of the first direction. Let's try to prove it in the other direction. Let's say that we can write it as a unique linear combination of the other n minus 1 vectors, then show that this condition would not be true. Okay, and the way to do that is to do it in the following way. What we can do is to take okay, so sorry about that. And so let's try to prove it in the other direction. It says if one of the vectors can be written as a linear combination of the other n minus 1 vectors. And so this is how we do it. We already know, so to prove it in this direction, we know that we can write Vi as a linear combination. So maybe we can write it as alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. And now if we can write Vi as a linear combination, then of course we can move these to the other side, and we have alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha minus Vi. So let's say we're moving Vi to the other side, and then plus dot 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 alpha n Vn equals to 0. So we now know that this equation is equals to 0 for some non-zero Ci. So if I set C1 to be alpha 1, C2 to be alpha 2, up until Ci to be minus 1, and dot 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 Cn to be equals to alpha n, then what I have is C1 V1 plus C2 V2 plus dot 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 Cn Vn. This linear combination is equals to 0 for non-zero, or rather we say for Ci's not all 0. Okay, And so I think we don't need unique massive. Okay. So that's the proof for 2. Can you hear me, Shoaib? Okay, perfect. Okay, and so let's move on to the next theorem. Okay, so this theorem says that if let's take some n vectors in Rn. So these are some vectors, so each of these vectors have n entries, they are vectors in Rn, and let X be a matrix such that it is made up of the columns of these x1s and x2s. So we actually have, let's suppose X is a matrix that looks like this: column 1 is x1, column 2 is x2, dot dot dot, column n is xn, right? And so we have essentially we have an n by n matrix because each xi has n entries because each of them is in Rn, and there are n of them because from x1 to xn, and so we have an n by n matrix. And the theorem says that these vectors will be linearly independent. So these columns essentially are linearly independent if and only if your matrix is singular, right? And that is actually quite easy to prove. So let's look at the proof for this. And the idea is that we want them to be linearly independent. And we know that linear independence comes from C1x1 plus C2x2 plus dot 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 Cnxn equals to 0, right? Linear independence comes from this if Ci's are all equals to 0, right? Then and only then do you have linear independence. And so the idea is at this point to just view this equation as a matrix vector product. So if I write this in terms of, so this is essentially nothing but summation Ci xi, where xi's are vectors, then this can be written in terms of a matrix vector product, right? So if I write it as x1, x2, dot dot dot, xn, and the right hand and multiply this by c1, c2 up until Cn, you see that what this equation actually becomes is it becomes a matrix vector equation. So let's call this matrix X, C and 0, and so we have xc equals to 0, which is a homogeneous system. And we know for a homogeneous system that the determinant is equals to 0, or rather it will have a only trivial solution if and only if the matrix is non-singular, right? So the idea is that, actually there's a mistake here, the vectors will be linearly dependent if and only if x is singular, right? So the idea is, now if you have a trivial solution for this system, trivial solution means that c1 equals to c2 equals to dot 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 cn is equals to 0. So you will get a trivial solution if the matrix is non-singular, and similarly you will get c1 equals to some non-trivial solution for a singular matrix. But of course, if the solution is non-trivial, then of course c1, c2 are not all 0, and that implies linear dependence. And so the idea is that if you consider these vectors, these n vectors, as columns of a matrix, then these vectors will be linearly dependent if the matrix is singular. So linear dependence is essentially the same as you having a singular matrix in your homogeneous system, right? And over here in this proof, we've just used the facts that we know about homogeneous systems and singular matrices and so on and so forth. Okay. All right. Okay. Next up, we have another theorem that says, let's say v1 to vn are some vectors in V. So we have a vector space V and we have some v1s to vn's, and they're saying that let V be a vector that is in the span of Vn. So let's say we have a span, we have some span of these V vectors, and we have this V vector over here, right? And so this vector exists in the span of V1 to Vn. And so V can be written uniquely as a linear combination of V1 to Vn if and only if V1 to Vn are linearly independent. Okay, and so the way to do this is to show two things. So the idea is V can be written uniquely as a linear combination. So linear combination of V1 to Vn if and only if you have Vi's are linearly independent, right? Or rather, the set that you have, the set from V1 to Vn, is a linearly independent set. Okay, and so of course, if we have a, let's suppose we had a linearly dependent set. So let's try to prove it from here to here. So we have two things. One is in this direction and the other proof is in this direction. And to go from this to this is quite simple. So if V can be written uniquely as a linear combination of V1 to Vn, then let's say V actually let's start from here. Let's do this direction first. So let's say these are linearly independent. Linearly independent implies that V1 C1 V1 plus C2 V2 plus dot 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 Cn Vn is equals to 0 implies Ci's are all 0, right? And so since V is in the span, since V is in the span of V1 to Vn, then we can write V as alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. And we have to show that this is unique. That is, I can't write it as we cannot have V equals to some other coefficients beta 1 V1 plus beta 2 V2 plus dot 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 beta n Vn. And to show that, let's do the following. So let's say we subtract these two equations, right? So let's assume by contradiction, so let's assume V can be written as this, so where pi's are not equal. So if we assume that V can be written in some different coefficients, then we can combine these two equations and see that alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. This is also a representation for V, and we're claiming that perhaps we can write it in some other representation where these coefficients are different. And if we equate them, we get beta 1 V1 plus beta 2 V2 plus dot 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 beta n Vn. And if we can bring these vectors to the left hand side, and we have alpha 1 minus beta 1 V1 plus alpha 2 minus beta 2 V2 plus dot 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 alpha n minus beta n Vn equals to 0. And now notice that this has become an equation of the form C1 V1 plus C2 V2 plus Cn Vn equals to 0. And because we already have linear independence, because we're assuming this and proving in this direction, so we have linear independence. And since we have linear independence, we know that this equation can only be 0 if all the Ci's are 0. So this is C1, this is C2, this is Cn, all of them need to be 0, which means alpha 1 minus beta 1 needs to be 0, which means alpha 1 is the same as beta 1. That even if you try to write it as different coefficients, these coefficients will be the same. Similarly, alpha 2 minus beta 2 equals to 0. This implies that alpha 2 equals to beta 2. And similarly, you have alpha n equals to beta n, and therefore alpha I is equals to beta I for all I from 1 to n, which means this indeed was a unique representation. So how did we do this proof? We did it by assuming that we have linear independence, then taking two different representations and showing that they were equal. If you take two different representations, and then you show that because of linear independence these must be the same, you have proven that this is unique. So alpha i's are unique, and that's the proof for the first theorem, the theorem in this direction. Now we want to prove theorem in the other direction, that is, V can be written as a linear combination uniquely implies that it's, so in this direction I want to prove that V can be written uniquely, blah blah blah, you know what the statement is. Then I want to prove this should imply that V1 to Vn is linearly independent. And the way I'm going to prove this, if you consider this statement to be a statement of the form P implies Q, then using the logic of contrapositives, I know that this is equivalent to proving that negation Q implies negation P. That if you don't have a linearly independent set, then you can't write them uniquely, right? And so instead of proving from this direction to this direction, I'll take the negation of this and prove the negation of this. And these two statements are equivalent. So it's easier to prove negation Q implies negation P, and since both of them are equivalent, I will have completed my proof. And so let's just do that. And so now I'm claiming that if linearly, if you have VI's, if you have V1 to Vn linearly dependent, then V cannot be written uniquely as a linear combination, right? So let's start from a linear combination. We have that, let's suppose we have some linear combination V alpha V1 plus alpha 2 V2 plus dot 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 alpha n Vn. Let's suppose we have this linear combination, a representation of V, because V was in the span of V1 to Vn. And now I want to show that this is not a unique representation, and the way I'll do it by showing that these are linearly independent. So since V1 to Vn are linearly dependent, then linear dependence implies the following: there exist Ci's not all 0 such that C1 V1 plus C2 V2 plus dot 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 Cn Vn is equals to 0. So you get a 0 vector even though these C1, C2, Cn are not all 0. And so let's call this equation 1 and let's call this equation 2, and notice if I add them together, so add these equations, so add 1 and 2, what do you get? So instead of writing 0 on this side, if I write 0 on this side, so notice what we have V plus, then from the second equation we have the 0 vector. This is the left hand side of this equation being added to the left hand side of this equation, equals to alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. And you also have addition, and let me write this on the next line so you can see how they connect. So I have the right hand side of this equation as this, and the right hand side of this equation is C1 V1 plus C2 V2 plus dot 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 Cn Vn, right? And now I can just add these equations up. This left hand side gives me just the vector V, okay, and the right hand side gives me alpha 1 plus C1 V1 plus alpha 2 plus C2 V2 plus dot 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 alpha n plus Cn Vn. And notice that this is another representation. This is V as beta. If I consider this to be beta 1, beta 2, beta n, then this is another representation of V in terms of the vectors Vi. So V2 plus dot 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 beta n Vn. So what have we shown? We've shown that V is not written uniquely as a linear combination of V1 to Vn. And since we've proven that this linear dependence implies that you can't write it uniquely, then you've shown therefore since negation Q implies negation P, therefore P implies Q, and therefore we have that if V can be written can be written as a linear combination, as a unique linear combination of v1 to vn, then v1 to vn are linearly independent, and that completes your proof. So just to recap this entire process that we did, from going from here to here I just used a direct proof, but to go from here to here I used the proof by contrapositive. So this proof was a proof by contrapositive. Okay. All right. Okay, let's say we're working in P3, the vector space P3. This vector space contains polynomials of degree less than and equals to 2 or less than 3, right? So it contains quadratic polynomials at best. It can contain linear, it can contain constant as well, but at most it can contain polynomials of degree 2, right? And so the question is, this is of course a vector space, and we want to show the question is, are these three vectors, so this is the first vector, let's call it v1, v2, v3, and the question is, are these vectors linearly independent? And the question boils down basically to this, that what are the solutions of the following: c1 p1x plus c2 p2x plus c3 p3x equals to 0. You make a homogeneous equation, right? And so if you have only the trivial solution, if you get only the trivial solution, that is c1 equals to c2 equals to c3 equals to 0, then you have linearly independent vectors. But if you get any non-trivial solution, so if you get any non-trivial solution, then you will have linearly dependent vectors. Okay, and so these vectors are actually polynomial, and so we just have to find the solutions of this homogeneous equation, right? And the homogeneous equation can be solved as follows. So c1 p1x, so c1, let me look at what p1 was. So p1 was x squared minus, let me just copy this from here, paste it here. So c1, we should do this, okay, and so this is c1 times p1 plus c2 times, let me just make some space for c2, and c3 times this is equals to 0. And let's just copy these. This is the second one, and this is the third one. Okay, and so we're looking for this one, this system, and we're trying to figure out whether these solutions are trivial or non-trivial. And so how do we solve this equation? Well, the first thing is, let's combine all of the like terms together in terms of the degree. So we'll have c1 plus 2c2 plus c3 x squared. So I combined all the degree 2 terms. Then next I combine all the degree 1 terms, minus 2c1 plus c2 plus 8c3. So let me check if I've done this correctly. c1, 2c2 and c3, correct, minus 2c1 and c2 plus 8c3 times x, and plus we have finally 3c1 plus 8c2 plus 7c3 equals to 0, right? Okay, and so the equation has become this. So c1 plus c2 plus c3x squared plus this x plus this, and all of this is equals to 0, equals to the 0 vector. Remember, this is the 0 vector. So on the right hand side, let me just write the left hand side as it is. So this is my entire left hand side, but my right hand side is actually the 0 vector, and the 0 vector in the P3 space is simply 0 times x squared plus 0 times x plus 0. That is the 0 polynomial. So all of these coefficients must be equals to 0. So we get, because the quadratic term on the left hand side is 0 and the quadratic term on the left hand side should equal the quadratic term on the right hand side, therefore we get the following equations. Equation 1, these coefficients should be 0. c1 plus 2c2 plus c3 should be 0. Next, minus 2c1 plus c2 plus 8c3 should be equals to 0. And lastly, 3c1 plus 8c2 plus 7c3 should be equals to 0. And at this point, notice that you just have a linear system to solve. This is simply ax equals to 0. And all you need to do is convert it into a matrix. Convert it into a matrix. Vector equation. So 1, 2, 1, minus 2, 1, 8, 3, 8, 7. Multiply it with c1, c2, c1, c2, c3 is equals to 0, 0, 0. This is just a homogeneous system, and all you need to do is, if you recall from the proof that we did above, that all you need to do, this system will have a trivial solution. This is a homogeneous system, and this will have a trivial solution if I call this matrix A, if and only if A is non-singular. So you just need to check whether it's non-singular or not. So up there, when we wrote trivial solution will result in a linear independence, we can just, over here we know that A is non-singular, and if we find A to be singular, then it will have a non-trivial solution, which will mean that the vectors, this p1, p2, p3 are linearly dependent. And so the question simply boils down to solving this linear system and just finding out whether this matrix is singular or non-singular. A singular matrix will give you a linearly dependent set of vectors. A non-singular matrix will give you a linearly independent set of vectors. And so I will leave it to you to check whether A is singular or non-singular. And if you have that, you will have the answer to the question whether these vectors are linearly independent or linearly dependent. Okay. All right. So before I begin this one, let's just talk about what we're talking about now. Finally, we're looking at the vector space C A to B, and actually we'll be looking at vectors in Cn minus 1 A to B. These vectors in this space are n minus 1 times differentiable functions defined on the interval A to B. So you have some interval A to B on which you have some function defined which is differentiable at least n minus 1 times. right? So if you differentiate it, you will get another function and it should be differentiable, right? So vectors in this space are differentiable n minus 1 time. Vectors in this space, these are just continuous. And notice something, that if you have vectors in, if you have a vector, let's suppose you have a function in Cn minus 1, that is, you can differentiate it n minus 1. If you differentiate this function once, then this is no longer in Cn minus 1 because you've already differentiated it once. So now this belongs in Cn minus 2. That is, you can differentiate it n minus 2 times at least, but not more than that is not guaranteed. Okay, and so here's the idea. We define, we have f1, f2 up until fn. These vectors are belong to Cn minus 1, that is, they are n minus 1 times differentiable, right? And so we define this matrix, and actually we define this determinant. So what have we done? We've taken all of these functions and we've written them down as columns. So the first row we just write the function as it is. In the second row we differentiate them once, so f1 prime x, f2 prime x up until fn x. And we keep doing that, and since we can differentiate them n minus 1 times, we differentiate these functions, all of these functions, n minus 1 times. So notice that there are n columns because there are n functions, f1 to f2 fn, and there are also n rows because you've differentiated them n minus 1 times. So from here to here you have n minus 1 terms and another row for the original functions. So 1, 2, 3 dot 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 up until n. So you have a matrix that is n rows and n columns, and this thing, the determinant of this matrix, is called the Wronskian, right? And so if you write it down like this is called the Wronskian of these functions. And we have a theorem about these Wronskians. And so here's the theorem. The theorem says that if you have a point n x naught such that the Wronskian at that point is non-zero, then these functions are linearly independent. Okay, so notice that it's not telling us anything about w equals to 0 when Wronskian is equal to. All it's saying is that if you find some point at which the Wronskian is non-zero, then you're guaranteed that the function is linearly independent. And so let's try to prove this. And so we want to prove that Wronskian being non-zero at some point implies linearly independent f1 to fn. And yes, I've written another note here again that where w equals to 0, if the Wronskian is 0 at every point, it does not tell you anything, because this theorem doesn't tell you what happens when the Wronskian is 0. All it tells you is that when the Wronskian is non-zero, then the functions are linearly independent. And so again, I'm going to use the same technique of proof by contrapositive. I want to prove that P implies Q. Instead of doing that, I will prove that negation Q implies negation P. And so let's figure out what the negation of Q would be. So Q says that these functions are linearly independent. That means negation of Q implies that if these linearly dependent, if these functions are f1 to fn are linearly dependent, that would imply that the Wronskian, now negation P implies that the Wronskian is 0 at all x naught a to b, right? Because this was saying that the Wronskian is non-zero at some x naught, then the negation of that statement would be that the Wronskian is 0 at all. There is no such x naught at which the Wronskian is non-zero. And so how do we prove this? So we start off from this statement. We say that f1 up until fn are linearly dependent, and that tells me there exists that exists C1 up until Cn not all 0, such that C1 F1 plus C2 F2 plus up until Cn Fn is equals to 0. This is the definition of vectors being linearly dependent, right? Okay. Now if I differentiate this equation, I get C1 F1 prime plus C2 F2 prime plus dot 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 Cn Fn prime. And again the same CI's work for this equation as well, because I'm just differentiated these sides. And so if I keep differentiating them over and over, I get C1 F1 n minus 1. Let's differentiate them n minus 1 times, plus C2 F2 n minus 1 plus dot 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 Cn Fn n minus 1. This is equals to 0. So what we have in fact is that now if I, oops, where did I go? Here we go. And so let me just copy this system. So I have this system which has a non-zero solution, right? So this system has a, for some C1, C2, Cn not all 0. And we just have to do one thing. We just have to view this as a matrix vector product. So if I write this as F1 dot 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 Fn, F1 prime dot 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 Fn prime, and up until I differentiated n minus 1 times Fn n minus 1, I'm writing this as a matrix vector product. So the matrix has these entries and the vectors are simply C1, C2, Cn is equals to 0, 0. And what you have is in fact a homogeneous system, but now we already know that this homogeneous system has a non-trivial solution, because it's true for some C1, C2 up until Cn not all 0. So this homogeneous system has a non-trivial solution. And if this homogeneous system has a non-trivial solution, that means the matrix, let's call this A, this matrix A must be singular, because only a singular matrix can give a non-trivial solution for a homogeneous system. Now if the matrix A is singular, what does that tell me? Matrix A is only singular if and only if the determinant is 0. And at that point you see that the determinant that you define F1 to Fn and F1 differentiated n minus 1 times, Fn n minus 1 times. And so this, which we originally defined to be the Wronskian, we know that this determinant must be 0. And so what we've done is we've shown that negation Q implies negation P, because we started off from linearly dependent set of vectors and we got the Wronskian to be 0. So this means that since F1 to Fn linearly dependent implies Wronskian to be 0, then by contrapositive, if the Wronskian is non-zero at some point, that would give us a F1 to Fn linearly independent. Okay, and that finishes the proof. So just as an example, consider this x square and x times absolute value of x in this. And so if I find the Wronskian of this, then the Wronskian of this is, you can see that the Wronskian if you find the Wronskian of this, that's equals to 0, but that gives you no information. You can check this example is in the book, and you can check how the Wronskian is equals to 0, but the point is, since the Wronskian is 0, it will give you no information, because the theorem only talks about what will happen if the Wronskian is non-zero at some point. So a 0 Wronskian will give you no information. You'll have to find whether the set of vectors is linearly dependent or independent based on some other method. So you will have to solve c1x squared plus c2 x absolute value of x equals to 0. You'll have to figure out what are the solutions of this equation. Okay, and I will stop at this point. And yes, Vinesh, you had some questions, you can ask them now. Okay, I'm going to wait for a few minutes if you have any queries, otherwise I'll just end the stream.